Okay, so welcome back to lecture 2 of elliptic curve cryptography. I'm going to pick up the pace a little bit. So remember that we started looking at elliptic curves last time. And for us, an elliptic curve is some smooth, projectively smooth cubic polynomial in two variables with at least one point defined over the base field. And we had, for example, this is an example of an elliptic curve, even though it's not in what we call the short Weierstrass form. But if you are, say, over the rational numbers or over fp for some p bigger than 3, then you can write your elliptic curves in this nice format. Okay, and do addition there. And I showed you how the equations to do addition on elliptic curves. And computers can do this very efficiently. And so the question is, though, we're interested in this set of the rational points. So these are all the points, EFP, are all the points on a given elliptic curve over FP. How many points are there? And a heuristic is that if you go back to the short Weierstrass form, well, I can take any x value, okay? So there's p options for x values. And once I have an x value, then I can check, is that a square or not? In fp, well, we have 0, which is a square. And then the other numbers, half of them are a squares modulo p, and half of them are not. Okay? And in general, if p is not 3, for example, many times cubic polynomials are actually bijections from fp to fp. So if you assume all of that just to get a heuristic, what happens most times, I have p options for x. Every time that x, the f of x, is a square, I will have 2 points because there is the plus or minus y. So it will be x and plus or minus y as points. However, it is a square about half of the times. And there should be a value, in general, if this is a bijection, there should be a value that f of x is 0, in which case the y, I don't have 2 options, is just 0. So that is plus 1. So if you multiply a half times 2p plus 1, this says that there should be about p plus 1 points on any given elliptic curve modulo p. Now, that is not true, but it is in essence true in that it is so except for a small error. And that is a theorem of Hasse, who proved that the error in approximating the number of points by p plus 1 is smaller, is a magnitude smaller than p, is at most 2 times the square root of p. And you can check that that is actually the case. I have, for example, here's an elliptic curve. And then, well, first of all, I've written an exercise in the set that says, when is this an elliptic curve? For what primes? So you should have just try to verify for what primes is this going to be an elliptic curve. But for example, for 3, it is an elliptic curve. There are 4 points, and that is exactly p plus 1. So the error, sure, the error is actually 0, but the bound holds. For p equals 11, there are 16 points. So the error there is minus 4, which is in absolute value less than twice the square root of p. So it works. And for example, modulo 4001, there are 39 points. And then you can check what is the error. So one problem is to do more computations of this sort to just check that those bounds actually hold. So it turns out that that elliptic curve, it is an elliptic curve modulo 4001. The number of points is 3939. It factors, that number factors as 3 times 13 times 101. We know that the group of points on an elliptic curve is actually an abelian group. And do you know why is that cyclic automatically? It doesn't have to be cyclic. These groups are not cyclic in general, but it is cyclic in this case. Do you know why? They're co-primed. So you can think about that. I'm going to also just leave that as an exercise, but that is essentially, that is the reason that you can prove from that and some bigger theorem in group theory that that is actually a cyclic group. So those points are actually generated by one point of a large order, 3939. So this point has that gigantic order. And we are actually going to, in cryptography, we don't want a point that has a large order that is composite, but we like points that have large prime order. So instead of taking this one, I'm going to multiply by 39, this one, to get a point that has order 101. And then we would do actually cryptography on the subgroup generated by this point of prime order. Okay? Because now that point, the multiples of that point, now it behaves like z modulo 101. And we can do things similar to things we've done before. But if you look at all the multiples of that point, I'm going to list here all 101 multiples. You can see again that it's very hard to sort of like predict what are going to be the coordinates of those points, and it give you one particular point. It's hard to figure out what was the power of Q or the multiple of Q that gave me that point. And this is where sort of like the idea of using cryptography on elliptic curves comes from. So by the way, every group of this sort, a group of points on an elliptic curve over a finite field, has this sort of group isomorphism structure. It doesn't have to be that it's cyclic in general, but in this case, it just turns out to be cyclic. So the elliptic discrete logarithm problem is problems of that sort. So so here's another point that is on the elliptic curve. So find a multiple of Q, being this Q is of order 101. What multiple of that actually gives me this point? Just like in the regular discrete logarithm problem, it just seems untractable in that I'm going to have to do a lot of addition on the elliptic curve, repeated addition, until I hit what point this is. It doesn't seem a priori that there is a way to use sort of like division by some sort of division instead of multiplication of the point to retrieve what point that would be. However, many of these statements are not proved. And we don't know that there is not a very efficient algorithm to solve this problem. We just think everything is built on hope, like rebellions, that we hope that there is not a quick way to do this, to break this sort of problem. In this case, x is 37. But in general, it's just tough to figure out what is that solution. And that is the discrete logarithm problem, the elliptic curve discrete logarithm problem. You have a prime, you have an elliptic curve, and then you have 2 points, and you want to find n such that n times p equals to q, or show that no such n exists. Again, these, if you just pick a pair of points on just some sort of like random elliptic curve over fp, that does not have to be a cyclic group, so you don't expect every time to have a solution of this kind. But when the cryptography is set up, usually there is a solution because we are working with the subgroup generated by a point of high order. So how can we solve a discrete logarithm problem? This is just set up as a discrete logarithm problem over a finite group. We can just do just brute force it. If G is in a finite group, G will have finite order. So there is the list of powers of G is finite. And if I want to know when does it hit H, I can just start doing powers of G until I hit H. That is the brute force algorithm. But there are better ways. So let me show you a better way of doing this, which is called, these are called collision algorithms. You'll see why. They're not so violent as this. But so for example, an example of a collision algorithm is Shank's baby step, giant step algorithm. So you have a group G, you have a generator or a point or an element of large order, n, and I want to solve G to the x equals h for some x. So I want to know, given h, I want to know what x does that. So what is the logarithm in base g of h? Okay, that's what we're looking for. And what you do is take n is 1 plus the floor of a square root of n. Notice that in here, if the order of g was capital N, I'm possibly doing up to n capital N operations. But in this algorithm, I'm going to be doing something like the order of 2 times the square root of n operations, or powers of g, which is much less. And then you build 2 lists. You build a list. These are the so-called baby steps. So some powers of g up to little n, where little n is this number again. And then you compute this auxiliary number. U is the inverse of g to the nth power. By the way, modulo p, inverting things, is very expensive in general, so you don't want to do this very often. But in an elliptic curve, inverting an element is actually very easy, because p and minus p just differ. The y coordinate is plus or minus p. Modulo p, if you're trying to do an algorithm that does a lot of inversions, modulo p, that is expensive, because you have to do a lot of Euclid algorithms. In any case, you build this list. These are the baby steps. You build this auxiliary number, and then you build this other list, which are called, these are supposed to be the giant steps. So you take h, and h times u, h is u squared, up to h to the un. And it turns out the magic of this is that there is a match. If you've gone all the way to n, at some point there is a match. And this, I'm going to leave it up to you. That's a neat little proof. It looks a lot harder than it actually is, but you can prove that there is a match in these 2 lists. You don't have to actually compute both lists all at once. For efficiency, you compute like this. You start building both lists at the same time, because if the hit happens very soon in the list 2, if this one is equal to this one, you don't have to compute this entire list first and this entire list first. So you can build both lists simultaneously. And there is a match, and that match will be some power of g is equal to h times some power of g. And it turns out that xi plus jn is the solution you're looking for. Okay? So there's a couple of problems in the homework set that we're asking you to find, what power of 65 is equal to 2 modulo 4003. Maybe yesterday you were trying to do it by hand, by brute force. Try to use this algorithm instead, and there should be a lot less operations to be done. And also, if you are into that kind of thing, which we hope you do, try to prove it, that there is a match and that this actually works. Okay, so here's an example. So take p to be a very large prime, 41. Take g to be 6. And that is a primitive root. So the order of g is 40. And let h be 2. I'm looking for a power of 6 that gives me 2 modulo 41. So take the order, square root it, 1 plus that, I get 7. And I build both lists. Okay? And then you see that there is a match right here and right here. You see that I have built both lists here, but actually I could have stopped here and here, basically. Or by the time I build this and I have already seen this, then I would have already found a match without having to go all the way to 7. So there is a match, and this is 6 to the 1, 2, 3, 4. No, this is g. So 1, 2, 3, 4, 5, and this is h to the u 2, 3. So it's 7 times 3 plus 5 is 26, and it turns out that 6 to the 26 is 2 modulo 41. Okay. So this is a improvement over the brute force, but it's still a square root of n over the order. The order is about the size of the prime itself. If the prime is of order of magnitude 2 to the 2048, their square root is still of the order a huge number. So there's still a huge amount of operations that even in this kind of algorithm you would have to do. Now, there are other methods that I'm not explaining here that work a little better than this, but not until we had some sort of like a quantum computer, this would actually be in trouble. Yes?
So the first list was powers of 6, and then you took them mod 41?
Yes.
And then how did you get the second list?
The second list is age. So did I do this right? Yes, so age, starting with the number that I'm trying to find, 2, and then 2 times u, and 2 times u squared, and then 2 times u cubed, etc. So the u, I pre-computed what is g to the minus n, which was the value of u here, and then go from there. So another question? Yes?
I know for like the regular discrete log problem, like Peter Shor has an algorithm that does it efficiently with quantum computers. Does that apply to the elliptic curve case?
Yes, I think also in the elliptic curve case, there would also be something that would break it. So it's not quantum safe either. The discrete log problem is not safe in the quantum world. Yes?
Could you say anything about the time complexity of that version?
I'm not going to get into, so the question is about time complexity and complexity theory. In these lectures, I'm not going to, we can talk about it in the problem sessions and so on if you want. So I can give you some reference for that. I'm just going to try to not look too closely at the time complexity. Just suffices to say that this is the magnitude of the brute force, is the order of operations is about the size of the prime, while here is the square root of the prime. That's the rough estimate.
So it doesn't contribute, the inversion itself doesn't contribute.
No, because there is only one inversion, and that is okay. All right, so here's another problem I'll throw in the set, a slightly larger prime, and try to see what happens. And here, by the way, this is not a primitive root. I think it isn't. Anyway, I'll throw that one in the problem sets for you to do. Now you can do as I explained the Shanks algorithm was for any discrete log in any group. So you can do it on an elliptic curve too. So take this elliptic curve, modulo 73, take this p and q, and I want to find what multiple of p gives me q. And I can do exactly the same thing. I can see what is the order of p. It turns out is of order 41. So the n here is 8. So I can build the list or start building the lists. I don't think I had to go all the way because here already I have it in the list. I have a match in here for I equals 5 and j equals 4. There is a match, and it turns out that 37 times p equals q. That's where the 37 came from. I think I had it in the previous slide or previously in the slides. This problem set up, and you can use the Shanks algorithm on these, and then also reduce the number of operations so you don't have to do like 41 multiples essentially of the point to figure out what multiple gives you q. Now there is a different version of the elliptic algorithm. Since you're just trying to crack something, you don't need something that is provably right every time. So this one, if you complete the lists up to 8, there will be a match. But you can do some things that tend to, as soon as you start getting like some high probability that you're going to find a success, you can do some other methods. So for example, there's a collision algorithm that says the following. So you choose random numbers, j1 through jr, and k1 through kr between 1 and p. How many? Combinatorics suggests that you have to have about 3 times the square root of p of those numbers. And then if you just choose some random set of numbers and then these random set of numbers, then when you find a match, and at some point you will find a match, so you can use the version of Shanks to show like where there would be a match. But in any case, when you find a match, then you can figure out what q is. Just solve for q in this one. So there are other ways to do this to crack logarithm problems, discrete logarithm problems. But so in here, by the way, notice that something that happened here is that there was no inversion. But again, inversion in an elliptic curve is kind of cheap. So anyway, you can also use the previous exercise and then just try this out and see what happens when you do something like this instead. Okay, so now we're going to move on to the actual cryptography. So the first cryptographic methods that were invented, the Diffie-Hellman key exchange, is based on this discrete logarithm problem. So we're going to talk about that. RSA, though, is built on a different problem, and then later in the fourth lecture, we'll talk about RSA and how to break it by using elliptic curves to factor numbers. So, so the Diffie-Hellman key exchange then later became the elliptic curve cryptography, which is a Diffie-Hellman but with elliptic curves. So let's explain how Diffie-Hellman works. Here are Hellman and Diffie, and who got the Turing Award for their work. And so here's how the Diffie-Hellman key exchange works. So this is going to be some public transmission. And what we do is we are just going to agree on a key and then use some other simpler method. So such as this key is going to be replacing what in 1917 in the First World War, spies were doing with the one-time pad. We just want to share one key that then we can use with a Vigenère cipher or something. But that key, because this works very efficiently, every time we send a message, we're going to change that key. So we keep doing this key exchange and translation of messages at real time. We keep changing them. So we fix a very large prime. Now, later, again, we will also talk about how to find very large primes, and a non-zero integer g modulo p that has a large order. It doesn't have to be a primitive root, but it helps if it has a very large order. And in many cases, it also helps if the order of the number itself, of the element itself, is prime. So Alice picks a secret key. That's a secret that you have to keep to your heart, A, and Bob picks their own secret key, B. Then you compute G to the A, which is capital A, and G to the B, and then you send that to Bob, and you send this to Alice. So you exchange the capital A and the capital B. You see now that the secret is now your secret little a and your secret little b is encoded under the safety of the discrete logarithm problem. Okay? Because publicly, we know what G is, we know what P is, and we know what A is. So I could just try to crack the code by solving a DLP. And then Alice will compute B of Bob to her secret key, B to the A, and Bob will compute A to the B. So his secret key and use it as an exponent on Alice's A. Why is that so? That's because those two coincide. They coincide because if you take, well, what is A prime? That's B to the A, that's G to the B to the A, so that's G to the B times A, which is G to the A times B, thanks to commutativity of multiplication in exponents. And that's G A to the B, which is A to the B, which is B prime. So they share this secret, but each one of them is able to compute it only because they have their own key to do that, and nobody else is able to compute this A prime and B prime. Okay, so that is their shared secret. And then after that, you use a symmetric cipher. Again, as I said, like some sort of like Caesar cipher or something more elaborate. So it turns out that if you use, for example, WhatsApp, I know WhatsApp uses elliptic curve cryptography. It uses the elliptic curve Diffie-Hellman. And what they do is after exchanging keys, we use something called AES 256, which is, as the way I understand it, is essentially an enigma machine, okay? Which is just a lot of different, a sequence of like 14 different rounds of transposition and mixes and shifts that you can sort of revert. You can encrypt it and decrypt it as long as you have a key to start with, and that's the secret. That's the key that starts the code. Okay, so that is the Diffie-Hellman, the traditional Diffie-Hellman. So take a prime, take a primitive root, and Alice picks a little a, Bob picks a little b, and Alice computes capital A, capital B, and then exchange that information. So send 390 to Bob, 691 to Alice, and then Alice can compute, where is it? Yes, 941 to the 347. Where did I get the 947? It's supposed to be, you're supposed to be raising Bob 691 to the 347. So this is not right. This is 691. So this is supposed to be 691 to the 347, and Bob computes 390 to the 781, and then they get a shared secret 470. Okay. So you raise, Bob takes this 390 to the secret key, and Alice takes this from Bob and raises to the power of A. Now, Eve is always listening. There's always people listening to all of these conversations. This is a sculpture called Eve Listening. In 1842, this sculpture was ahead of his time. So in any case, there is always, this is all transmitted in public channels. So there are people listening, so you have to be careful of like what the information do they have to try to crack this code. So in here, Eve knows P and knows G, will know A, because that is being sent in public channel, and will know B. And you have to assume that everything that is being transmitted is perfectly readable by anyone, right? Everything that is transmitted, you have to assume for the security of these methods that everyone has all this information available. So what can Eve do? Well, Eve can Eve knows that this 390 is a power of 627. So Eve needs to solve this problem. If Eve figures out A, then she can play the role of Bob and just raise B to you could play the role of Alice, right? If Eve knew the little a, then it can use the information of Alice to decode everything. Or similarly, if Eve can crack this log problem, if can find B, then she can take the role of B, of Bob, and solve the problems. So this would crack the security of the process. Or there is another possibility, which is that at the end of the day, the key, if you go back to how we computed the key is also G to the AB. So there's a different strategy, which is that if I know G to the A, if I know G to the B, can I compute G to the A times B? And that's not how exponents work, as much as calculus freshmen might want to. That is not how they work. But is there a way to compute this out of these two numbers, especially if you're working modulo P? Well, we hope there isn't, but we don't know. What we know is that, so what we call the Diffie-Hellman problem is exactly that, is knowing G to the A and G to the B, can we compute G to the A times B? That is the Diffie-Hellman problem, and as I said, that is weaker than the discrete logarithm problem, because there is a way to solve this by figuring out where A is, what B is, and then computing G to the AB, right? However, it is not known whether the Diffie-Hellman problem is stronger than the DLP. In other way, is there a back door to compute this out of these two numbers without having to crack the DLP? That's an interesting question at the level of middle school. Okay, so now this is a toy example in the current guidelines. P has to be some like 2048 bits, so something in the size of 2 to the 2048. G is suggested to have some prime order of at least 256 bits, so the order of G being something like 2 to the 256. And G might not be, you might get away with G not being a prime order, but it has to have a very large prime factor, okay? Otherwise, you're toast. All right, so can we do this in elliptic curves? Yes, we can in the same way. So the Diffie-Hellman key exchange can be also basically set up for groups. And you can essentially do the same thing. You take a large prime, you take an elliptic curve. Now we're working over the points on the elliptic curve. Take a prime P of large prime order, and Alice is going to do the same. She's going to choose a secret key, an integer, and Bob chooses an integer and they compute their multiples of P by their secret key, QA and QB. And then QA is sent to Bob, and QB is sent to Alice. And now they can compute a secret key, which is if I multiply by NA, the point of Bob, or the point of Alice times the secret key, I get, because of the fact that this is a group, we actually get that is just NA times NB times P. And this is a secret key. Yes?
Is there a reason why in the case like over FP that we picked a primitive root versus now we're just picking on with a large prime?
We don't necessarily pick a primitive root. We need the order. So G, here I picked a primitive root just because I wanted something with a large order. But you don't have to pick a primitive root. The guidelines say you take G. Ideally, G is just some element of prime order. So the primitive roots have order P minus 1. So P minus 1, that order is not prime. So typically, you actually don't pick a primitive root. You just hope that P minus 1 has another factor that is very large. So for example, that's where Sophie-Germain primes come in. Because if you have a Sophie-Germain prime, so if P minus 1 is 2 times Q, then that Q is going to be huge, right? So that is one way where Sophie-Germains come in handy to have very large Sophie-Germain primes. If this is a Sophie-Germain prime, maybe I think I always get safe primes and Sophie-Germain primes confused. I think this is a safe prime in that P minus 1 is 2Q with Q very large and prime. Then you can take not the primitive root that would have order 2Q, but you have the option of taking G, the element or an element of order Q, which is of the size of Q, so Q is P minus 1 divided by 2, so very large. Okay? So this is the secret key that Alice and Bob share. And as I said in the previous lecture, these are very simple ideas once you've discovered them, right? It's ingenious to use this and to think of these ideas, but now it is just, there's literally nothing to it, how these work. And I love this topic, cryptography, because they are based in such simple ideas. So, who is going to come up with the next simple idea? Or a simple idea to break these things without having to use the discrete log problem. So both in creating new cryptographic systems or coming up with some idea to break them, they're very interesting problems. So here is an example. Take our favorite elliptic curve over F73. Take this point. It has order 41. Well, one question, first of all, is what is the group structure of this group? But this point has order 41, and we're just going to be working, the elliptic curve cryptography is happening with the multiples of P. So it doesn't matter if there are more points, we're just working with multiples of P. take secret key 11, secret key 17, compute 11 times p, send it to Bob, compute 17 times p, send it to Alice. And then take Bob's point, multiply it by 11, take Alice's point, multiply it by 17, and you get a secret key. Okay? Now Eve is there listening. What does she know? Well, she knows a lot because this is all public information. And now QA and QB are public. So she just needs to solve this problem, n times this number, this point is this point, or this problem, some multiple of this point is this point. So 2 elliptic curve logarithm problems, discrete logarithm problems. Solving any one of them would allow her to play the role of one of the two, and either do some sort of like phishing attempt to start communicating with somebody, pretending you are the other person. Yes.
Why do they need to make those information public, like the information about elliptic curves and the time? Like if they can keep those things secret, why can't they keep that elliptic curve secret?
Because that is a very good question. Because this is all set up remotely. You and I start talking on WhatsApp. We're not going to meet here first and agree, oh, what key are we going to use? What elliptic curve are we going to use now? We want to do it remotely. You're abroad, I'm here, and every time you don't do this once, the elliptic curve, you might fix an elliptic curve, but then these choices of keys are being changed all the time, right? So the key in the safety also is that maybe you can run a computer and break one of these discrete logarithm problems, but I think in the order of magnitude on that is suggested, the computer might take years to break one, when we are actually changing that key all the time. Every time we send like a word, a message is encrypted in a different way. So it wouldn't make sense for someone to try to even start cracking with the methods we know. Yes?
I also think just the general principle in cryptography is whether or not you want to make it public, you should just assume that your choice has been cracked by some eavesdroppers, rather than deliberately want to.
Yeah. As I said, it's easier to, and for safety, assume that all of these bits are completely public information, because then you're already counting on that. But there is a different problem that Eve could solve, which is, given this multiple of p and given this multiple of p, find this multiple of p. Okay? So I don't know n, I just know this point. I know this is a multiple of this point, and now I want to know what is that multiple. Okay? So that is a different problem, and again, we know that the DLP, the discrete logarithm problem, can solve the elliptic curve Diffie-Hellman problem. So the DLP is stronger than DHP, but it is again not known whether the elliptic curve problem is stronger than the discrete logarithm problem, whether there's a different way to solve this problem that then later can crack also DLP problems. Okay? Now, the key, once you start talking about actually implementing this, you don't want keys to be very large. And here one problem is that the key actually has two components. Each one of those is a number modulo p, so it's a number as large as p. So now the key has sort of like double in size from the original Diffie-Hellman problem modulo p. And you don't want that, but that's actually not happening here, because on an elliptic curve, if I give you the x coordinate of a point, then there is, and it is a point, then there's only two options for y, plus or minus 34 in this case. So the secret is not 6834, the secret is 68. Because when Alice sends 39 to Bob, so instead of sending QA, then Bob knows that the point for Alice is 39 plus or minus 17, so it's plus or minus that point. But when we multiply these points, that plus or minus will give me that the secret key is plus or minus k and they have the same x coordinate. So the x coordinate is the key, not the entire point. Okay, so that way the key is just one number modulo p instead of two numbers modulo p. And the reason why we use elliptic curve cryptography over RSA is that because of the arithmetic of elliptic curves, it includes some level of security in how points are computed that allows you to use smaller keys. So you can use keys of about this size, and that would be the equivalent of a key of about this size in RSA. So it just saves you sort of like memory and computing power if you're using elliptic curve cryptography. Now, we've talked before, I want you to try, I'll set up problems to try other groups. So what happens with other groups? For example, if you want to get more into arithmetic geometry, then you should learn about abelian varieties, Jacobians of genus 2 curves. Those are good, but then the problem is that if you replace an elliptic curve by a genus 2 Jacobian, then the computations start to get heavy. The actual addition of points and so on, that starts to get adding to the complexity and to slowing down the algorithm itself. So elliptic curves is some sort of like sweet spot of complexity without adding a lot of computing power. Okay, so it looks like you don't get a lot of benefit from going up in genus, for example. All right, a different kind of public key cryptography that was invented based on the difficulty of the discrete logarithm problem was the Elgamal public key cryptography described by Tahir Elgamal. And so in that case, we're actually going to do cryptography. We are actually going to encrypt messages with this method directly instead of just exchanging a key and doing a different level of cryptography later. We're actually encoding messages here. So you take a prime, again, a very large prime. G is, again, of a large prime order. Alice is going to set up. So this cryptography is, again, based on sort of like Alice is, I don't know, a credit card company. Alice is American Express. And you are going to communicate to Alice, right? You're going to have to send messages, your own credit card number to Alice. So Alice just sets a system for people to send messages that then she is going to be able to decrypt. So chooses a private key, computes capital A, G to the A. So here is where the DLP comes into place, and publishes P, G, and A, and waits. Now Bob is going to send a message and wants to encrypt it to Alice, so only Alice can decrypt it. So the message is some number, modulo P. Now this number can be just some sort of like text string that is like, you know, like A is 01, B is 02. You can just create a way to a word, make it into a number. So you send a number over. You choose a secret K modulo P, some random number K, and you use 1K per M. We'll come back to this because it came back to bite a few very important people not to do this. So you choose 1K per message, and then you compute a pair, C1 and C2, like so, and send this pair C1, C2 to Alice. And now this is the encrypted message, and Alice is supposed to be able to decrypt it. Alice computes X to be C1 to the A, her secret key, inverse, and Y is C2 times X. And it turns out that C2 times X is M, is the message that Bob wanted to send before it was encrypted. So this is, why is that so? Y is C2 times X. X is C1 to the A inverse. And then if you translate what is C1, that is G to the K, and C2 was M times A to the K, and if you keep translating what everything means, everything cancels out, and you get M back. Okay? And I'm not going to go over the role of Eve here, but you can think about like what does Eve know and what we would have to break. And in both cases, you either have to either break, for example, something like this, which is a discrete log problem to find out what little k is, or you have to break that. So there's several ways to do this problem. You can set this up exactly the same way in elliptic curves. So you take an elliptic curve, modulo p, and then you have Alice sets up a private key, a private multiple of p, and publishes that elliptic curve prime and that point. Now Bob is going to choose a plain text, so a number that is the message, but that number now has to be a point on the elliptic curve. Now this is a little bit more complicated. Before I could just sort of like translate, like hello or Alvaro. Alvaro is 0, 1, and then L, whatever number that is, and I can translate it into a number. But now that number is not going to be the x-coordinate of an elliptic curve necessarily, of the elliptic curve that Eve has chosen also. So how do you do that is to add some padding at the end. So every message comes with a message, and then the last digits, the last whatever 5 digits is a padding, and that padding is just whatever number you need to do so that mn as a text number becomes a point on the elliptic curve. Is that going to work? Well, yes, because when we saw the count of how many points are there on an elliptic curve, if I just write this number and it doesn't work, change the last digit from a 1 to a 2 to a 3 to a 4. There is enough points on the elliptic curve for every x value. You have like a 50-50 chance that it will be a point on the elliptic curve, that x coordinate will be a point. So you'll soon enough, with this padding, you'll find a point that has that information. And as long as in the encoding, Alice has set this up so people are encoding, so you know how to retrieve the m out of a number like this, then it works. So again, you choose a random k, and you choose the pair, and then a ciphertext. And Alice can decrypt, because now the message is C2 minus NA times C1. You can see here how it works out, that when you translate what C2 and C1 are, these things cancel out, and you get the point back. That is the point M that encodes the secret message. Okay? And again, the security of the problem resides on essentially on this, on the elliptic curve discrete logarithm problem. So here's an example of that. You take the elliptic curve that we were using before and the point we were using before, choose a secret key and a secret point, and here Bob is just sending the message 1. Like when you reply to your doctor's office and you want to like, yes, confirm, you just send a 1, right? So that is encrypted too. So that message is encrypted as a 1 and then a padding. I'm going to put a 7 there just so 1, 7. 17 is actually a point on the elliptic curve. And now choose a random k, 8, compute my C1 and C2. And C1 and C2 is a pair of points on the elliptic curve. Send those over to Alice, and then just Alice can decrypt by doing this computation and figure out that the message was 1726. So the message is a 1. Yes?
So it's possible that you might need to add more than 1 digit for padding, right?
Yeah, for sure. In here, I think you could do sort of like the computation of like how many points, how many x coordinates are actually x coordinates of points on an elliptic curve. And if I go through 10 through 19, is it possible that I don't have any x coordinate that is one of those? I think there should be a point. Just by counting the number of points, there has to be one that is a point on the elliptic curve. I'm not sure on this, but you would do that computation, like how am I going to set up the message encoding so that there is enough room.
More like how does Alice know which digits to truncate?
Yeah, Alice sets that up. So, and in the setup, I didn't put it here, but the setup of how to encode messages as points on an elliptic curve, that is sent, that is part of the setup, not part of the encryption. Yeah.
So for Diffie-Hellman, we could forget the y coordinate of
Yes.
Is that still the case for Algol?
I don't think so. I don't think so. I think in the Elgamal, you do have, when you're doing the addition of these 2 points, you do need the y coordinates to be correct. So this is a little heavier for sure. Okay. But it's also doing already the work of encoding messages directly. So you expect that the information is going to be a little heavier too. Okay. So let me finish with a different application of this same method, which is the digital signatures. So now you also, now more and more often, you want to send a document and make sure they know that you are the one sending that document, right? That you are the right person who is sending that document, so nobody can impersonate you as, I don't know, sending your social security number or something. So more and more often, you get documents that are somehow encrypted, the messages are encrypted themselves. So here's how you do a digital signature. I'm just going to do the elliptic version directly. You take a prime, you take an elliptic curve, and a point of large order, and Sam is going to sign their document by choosing a secret s, a value of s, between 1 and q minus 1, the order of g is q, and compute this multiple of g, s times g, and publish that v. Now, Sam can, that is their public information to prove like this is me. I'm signing this because I'm the one that knows where v came from. And now you choose your document. This q is very large, so sometimes you can encode the entire document as a number modulo q, or you can encode a beginning of your document, the first however many characters, you can encode that as a number modulo q. So you choose a document that you're going to sign. You choose an element E mod q, again, something that is random, and then you find E times G and 2 numbers, S1 and S2. This is the X coordinate of that point, EG, and you publish your signature, D, S1, and S2. And it turns out that Victor now receives this document and wants to verify that that's you, so computes 2 quantities, V1 and V2, and then the point V1G plus V2V computes the X coordinate, and if that matches your S1 in your signature, then that was you. Okay. Again, the power of this resides on here 2 instances of the elliptic curve discrete logarithm problem. By the way, the slides are going to be in the GitHub, so all of this, well, you can access later. And it works. It works because if I multiply V1G plus V2V, and you do just the algebra of it, you get EG. And EG, the X coordinate of EG was what S1 was. So you can check that this X coordinate is equal to that X coordinate, and that's the verification. So the X coordinates coincide. I have here an example of a verification. So let me just point out again that this number, you're supposed to be changing that number every time you send a document. And that had catastrophic consequences. Well, catastrophic for Sony, not so catastrophic for PlayStation owners. If you remember, I don't know if this was in 2006 this happened, but I remember when like the before and after PlayStation games were cracked, and then you can like get bootleg copies of, not me, people were villains and getting bootleg copies. But what happened was that they were using the elliptic curve digital signature algorithm, and they set it up wrong. Like these PlayStations, they did not have connection to the internet, so they had to set up once the elliptic curve digital algorithm. And what they did is that E was fixed. And if you fix E, then you can crack it, because if you have now 2 different documents, you have 2 different games that they are authorizing to be PlayStation games, you just check 2 games, then you can compute the signature, you can look at the signature of one, you can look at the signature of the other, and compute what the S value was in the setup. Remember that the S value was the most secret part of the whole thing, was the key for Sam. So if you repeat that number even twice, then you can figure out what the secret key was. So if S was fixed and the E was fixed, then you can crack it. And somebody figured this out, they cracked it, and then, well, the PlayStations were there. They were not going to say, like, nobody can play PlayStation anymore until we release PlayStation 4. They were just out there, and like games were able to be, they were able to crack them. Now, this happened again. So there was, when Bitcoin started getting popular, there were all these crappy apps that were doing crypto business on Android phones. And there was a library they were using to do the elliptic curve digital signature algorithm, that they were using that library and then using the digital signature to trade Bitcoin. And then somebody realized that, okay, here they were not as dumb as Sony and PlayStation, but they were nearly as dumb in that the E value was some very easy, I forget if it was like some linear function or something, it was like some very easy function that was changing and that it was cyclic. It started repeating itself, so they could figure out what the pattern was or what the function was, and then crack that. And it was like I believe one of the first Bitcoin heists, which was somebody that learned elliptic curves at some point and knew how this worked to crack this code. So I think I will. Let's just say that what we're going to do also in some of the problems is let's replace G by other finite groups, and let's try to implement the Diffie-Hellman in other groups. So I'm going to suggest some groups, but then I would also love for you to come up with groups and then just try to see how it works in practice in some other groups. The suggestions that I have is like do a dihedral group and do some Jacobian of a genus 2 curve. But I would love to see other things like some group of 5x5 matrices or something. And play yourself, you should play both roles. You should play the I'm going to encrypt and also think like, well, how secure is this multiplication in this group? Is there some sort of like easy way to get logs? For example, if you do cryptography in Z modulo P under the addition, then inversion and everything is very easy to crack. Okay, so you don't want to use a very easy group, for example. So let me, I think, stop there, and I'll take questions after I stop the video.